Hello everyone. In this video we will be discussing pressure and the role it plays in fluids. Pressure itself is the measurement of how much force is being applied over an area, or in other words, how strongly a force is distributed. The standard unit of pressure is pascals, and the formula based on the definition of pressure is force divided by area. While this is the fundamental definition of pressure, we see it primarily utilized in fluids. When discussing fluids, it is important to understand the quantity called density, which measures how much mass a substance has per unit volume. Or in other words, how tightly packed that substance is. The standard unit for density is kilograms per cubic meter, and the formula states that density equals mass over volume. Now that we understand density, we can discuss the pressure that an object would feel by being submerged some depth in a fluid. This pressure is due to the weight of all that fluid that is above the object and can be found using the formula where pressure equals some initial pressure that's at the top of the fluid, plus the density of the fluid times g times the depth that the object is in that fluid. Let's start with an example that relates to the definition of pressure. Find the pressure exerted on a wall by pushing against it with a force of 20 newtons if part A says we press with the surface of our palm, which has an area of 0.0162 meters squared, and then part B says we press with the tip of a nail, which has an area of 0.000009 meters squared. In both parts, we know the force is this 20 newtons, and we also know an area, which means to find the pressure, we can simply use the formula force divided by area. Let's see how this works out in part A. Pressure equals the force, which is 20 newtons, divided by the area, which is 0.0162 square meters. Doing this calculation, we get about 1,234.6 pascals. So there would be the pressure against the wall from our palm. Now what about part B, where we're using a nail? The force is still 20 newtons, but now the area is this 0.000009 meters squared, which gives us about 2,222,222.2 pascals of pressure. Notice that despite applying the same force on the wall, we find a much higher pressure from the small tip of the nail. This is because the same force is much more focused into that small area, making the nail able to puncture the wall much easier than we would be able to just using our whole hand. Now let's see what a pressure problem involving fluids looks like. A manometer is a device used to measure the pressure of a gas. A U-shaped tube is connected to a container of gas on one end and open to the atmosphere on the other. If the liquid in the tube is mercury, use the measured heights to find the pressure of the gas. Note that the density of mercury is 13,600 kilograms per meter cubed. In this problem, we are interested in finding the pressure of the gas, but we only have an equation that finds the pressure some depth in the fluid. This is where some properties of fluid pressure comes in to help us. One of the things that we must be aware of is that if two substances, such as this gas and the mercury, are in contact with each other, then they both have the same pressure at that point of contact. So this point here, where the gas and the pressure are in contact with each other, must mean they have the same pressure there. The next piece of the puzzle we need is that for a single connected substance, the pressure at the same heights must also be the same. So whatever the pressure of the mercury is at its highest point on the left side that I've highlighted, must be the same as the pressure I would find looking at the same elevation of the mercury on the right side of my tube. Now that I've boiled down this problem to just finding the pressure that's at this tick mark here on the right side of my column, do I have enough information to find that? One thing I want to be aware of is that the right side is open to the atmosphere, so there's some P0 at the top of my mercury, which is equal to 1 atmosphere of pressure. Then if I can find what the depth from the top to that tick mark is, I can use the equation where pressure equals P0 plus density times gravity times that depth. By reading off the heights that they've given me, I can see that if I take the 3 centimeters and add that depth d to it, they should combine together into the full 10 centimeter measurement. Or in other words, the depth will be the difference between the 10 and the 3, which is 7 centimeters. Now that I know the depth, which we will want to convert to meters, let's plug things into our pressure equation. I know the pressure at the top of this mercury is just atmospheric pressure, which is 101,000 pascals, plus the density of the fluid, which I'm using mercury, so I need 13,600 for the density, times G, which is 9.8, times the depth, which when I convert to meters is 0.07 meters. Doing this calculation gives me a pressure which is 110,329.6 pascals. So once again, this is the pressure we would feel 7 centimeters deep into this mercury, which was open to the atmosphere. But since that elevation of mercury on the right side is the same as the elevation that is connected to the gas on the left side, that makes this pressure also the pressure of the gas.